In today's video, we're going to be talking about how to use ROS 2 with the Viam Rover. Now, if you recall, the Viam Rover is a robot created by a company called Viam. The very nice thing about this Viam Rover is that it comes almost fully assembled and has a lot of great features, such as motor drivers, wheel encoders, and accelerometer, and even a camera. Because of all these great features on the Viam Rover, it is the perfect platform for us to explore with using ROS 2. I'm not going to be covering how to get started with ROS 2 because I think there's lots of great tutorials on YouTube for that, but we will be looking at how you write a ROS 2 node and you interface that with actual hardware. In terms of low-level control, we will be using this libgpio library that I've created, which is basically a wrapper around pigpio, and I've used that library in a number of other videos. If you enjoy today's video, please like the video, subscribe to the channel, and share with your friends. As I mentioned in the intro, we are not going to be talking about how you install ROS 2. We're going to basically be starting from a pub/sub node using C++, and we're followed through their instructions on how to do that. I will say that we are using the humble Hawksbill distribution of ROS 2, and of course we're running this on a Raspberry Pi. When we create the ROS 2 package, ROS 2 node, we get a package XML and we update that. We need to use geometry messages because we want to control the robot using the twist message. And then here's where we are using ROS 2 CPP or C++. We are using the libgpio library for this. I have split that out into a separate repository and then incorporated it in this package. So when you go and find this Viam Rover package on GitHub, it has everything self-contained. You will still have to install pigpio though. In order to build the libgpio library, we do include that in the CMake list file for the ROS package. So most of this is auto-generated from the ROS 2 tools, but then we go in and manually modify it to add the third-party subdirectory and then link against libgpio. So the libgpio library is located under third-party libgpio. We've also added in a CMake list file here to build everything under third-party. One thing you'll see here is we have this libgpio use pigpiod if2. I've updated libgpio to actually use the daemon interface for pigpio. The pigpio library actually has two different ways you can interface with it. In most of my previous videos, we were using the standard pigpio C interface mechanism. Most of my videos will tell you that you need to do like sudo run the application. That's because when you use the standard pigpio library, you need to be root in order to run the application because it accesses some restricted features in order to use it. The other interface that this library provides is this pigpio daemon interface. When using this interface, there's a secondary daemon that's running with that root access, and then you use functions to communicate with that daemon. There's actually one application that's running that is the pigpio daemon, and then our application sends commands to that daemon for it to interface with the hardware. One of the reasons we do that daemon is because with ROS, running the actual node with root access is a little bit tricky. I tried a number of things to get that to work and I couldn't. So the easier option was to simply use this pigpio daemon interface. If we look at the libgpio library, we'll see that there are now these two subfolders, pigpio and pigpiod_if2. The pigpio folder contains all the code for communicating with the standard pigpio library. We include and does all the functions such as GPIO PWN. You'll see explanations on these functions in some of my other videos. And then the pigpiod underscore if2 folder is where we do the work using the daemon interface. So they're very similar, but there are some slight differences. We can see here that we use this set PWM duty cycle function when we're using the daemon interface, and we use this GPIO PWM function when we're using the standard pigpio interface. You don't have to worry about which one you're using. The way the code is structured is it will just use the correct version of the functions, but you do need to specify which one you want to use. So by default, it will use the standard pigpio interface, and you need to specify if you're trying to use the daemon interface. And you do that by specifying this CMake define. That's all set up in the CMake list file for libgpio. So again, you don't have to worry about it, but you do need to specify that in this ROS node. So you'll see in this third-party folder, the first thing I do is I set this variable to on, so that when we build libgpio with this command, it's going to build the libgpio using the daemon interface. That's available starting from version 0.2 of the libgpio library. Then in terms of the actual ROS node, we have the main function. This is our actual application or the node. This is pretty straightforward, standard ROS2. Initialize the ROS2 node. We say the node that we're going to run against, and then we shut it down at the end. This looks very similar to this main here that is from the tutorial. We simply split the main and the node into two separate files. So the motor control node itself is pretty standard ROS2. We have our node, we have our subscription, we have our callback for the subscription, which we'll see all in the C++ code. And then we're going to be using the libgpio motor driver class for controlling our motors. So we need two motor driver instantiations, one for the left motor, one for the right motor. And here we have this watchdog, which we'll be using to monitor that we are getting commands for motion within a timely manner. When we go to the source file, we'll see that we set up the left and right motors using the pins. These are the pins from the Viam Rover, and if you look at the motor driver video I have, you'll see where we get these pin numbers from. So we instantiate the left and right motor using those pins. We set up our subscription, so we're going to subscribe to a topic that is just called command vel, and every time we receive a command or a twist message from that topic, we will execute this handle command vel function. Then we set up our watchdog, where if we don't reset the watchdog within 2 seconds, then the timeout callback will be executed. One thing here is that we start the watchdog as timed out. Sometimes you want your watchdog to start off in a timed out state, and sometimes you want to say, okay, it's not timed out until the full 2 seconds have transpired. For us, we're saying, hey, the watchdog is timed out until you receive the very first command, and then it will start timing. When we talk about motion within a robot, one thing we have to consider is what happens if you don't receive a next command. So let's say I get a command to start moving forward, and then I don't receive a command for another 10 seconds. Should I continue to move forward, or should I stop? From a safety perspective, the safest thing to do is to stop. So there needs to be some kind of timeout that says, well, you should be continuing to receive commands to move. Otherwise, assume that the person giving you those commands has gone away, and you should try to stop so that you don't run into a wall or crash into something, causing damage to a person or some other property. So if you don't receive a command within 2 seconds, the watchdog is going to trigger a callback, and that callback is going to stop our motors. So then when we receive the twist message, we need to convert from the twist message into percent effort. If you recall from my video on the motor driver, the motor driver functionality inside of libgpio is based around this concept of effort, or effort percent. The example I always give relative to what effort means is like in your car, if I told you to give 100% effort, you would push your gas pedal all the way down to the floor. But if I told you to give 50% effort, you might put the gas pedal to 50% towards the floor. In terms of our motor driver, the way we define effort is 100% effort means give it 100% PWM duty cycle, and a 50% effort would be a 50% PWM duty cycle. However, the twist message gives values based in velocity. And if you go look at the ROS2 twist message definition, we'll see that there's linear velocity and angular velocity. Now, one of the trickiest things I find about ROS2 is that the units are not clear from the message definitions. So you may be wondering, well, what velocity? Like, what's the units of velocity for linear? There's linear XYZ velocity and then angular XYZ velocity. So there is this rep 103, which tells you what the standard units are. I, again, personally think it could be a little bit more clear as to what they are, but it does at least provide that. And they use SI units for everything. So your first assumption when you're dealing with ROS2 messages is that it is SI units. So what we need to do now is convert the twist message, which is going to be in meters per second and radians per second, into this percent effort. And we got to figure out what that means. And in general, that's one of the things we just have to be very mindful of when it comes to robotics. Some elements will be given in velocity, and some elements may be given in some other unit like percent effort. And we have to do this conversion and understand that conversion. Now, I don't know what the max velocity of this vehicle is, so I'm just going to say, hey, whenever you get any velocity, we're going to move at a constant rate. So I'm going to take this geometry twist message, say if the linear x velocity, which is the velocity moving forward, we're going to set both motors to forward, and then we're going to give just a randomly chosen 60% effort. What we would ultimately want to do is to map this linear x value to some effort. So let's say the maximum speed of the vehicle could be 2 meters per second. So when 2 meters per second is received, we should provide 100% effort. If 1 meter per second is received, that should map to 50% effort. For now, we're just going to get basic motion working. So any velocity in the forward direction will translate to 60% effort forward. Any velocity in the negative direction, which means move backwards, we'll move backward at 60%. If we get a zero linear velocity but a non-zero angular velocity around z, we will rotate at 50% effort. And then if we get some value that's unexpected, just stop the vehicle. So in terms of supported motion right now, we can move forward, we can move backwards, we can rotate to the left, we can rotate to the right. The Viam Rover is a differential drive vehicle, so we are able to rotate in place to the left and the right. We actually see that we reset the watchdog here when we get a new twist message. So in terms of control of the vehicle itself, it's fairly straightforward. There isn't too much complexity here. The most complex thing is this mapping from the twist message to the percent effort that we need to do. One thing you'll notice is in Visual Studio Code, we have everything being found ROS2 related. The way that I set that up is that there is a ROS extension. I find that the 0.9.6 preview version works a little bit better. So I am using the preview of 0.9.6, but by installing this onto your Visual Studio Code, you now get functionality for finding all of the relevant ROS2 related headers, so that Visual Studio Code can do some of that in autocomplete IntelliSense for you, and you don't get red squiggly lines everywhere. If you want a refresher on how to set up your Visual Studio Code to do remote development, please look at that video that I have posted. So all of this code right now is sitting on my Raspberry Pi on the Viam Rover itself. So we're developing on the Viam Rover. The Raspberry Pi on the Viam Rover has ROS2 installed. We're writing this code that's sitting on the Viam Rover, and then when we build and run, everything is going to be running on the Viam Rover itself. So now that we've looked at the code for the motor control node, we have to build the code and then run it and test it. So to build, ROS2 comes with its own build system called CallCon, and we run that build on our node. We're at the top level of my ROS2 workspace, and we're going to run concall build, and then we're only going to build the Viam Rover package, which is this package that I'm working on here. One thing I ran into was that just running CallCon build without selecting a package would cause some instability in the build. Doing a quick Google search, I found that when you do CallCon build, it will attempt to build a bunch of things in parallel, and you may run out of memory. So what I found is either to just build the package directly, we're using the packages select flags like I am here, or to use this sequential command here. So you go ahead and build the packages using directly just the Viam Rover. I've built this before. We then want to make sure that we do source the setup, so we can have access to that package now that we've built it and it's been installed. And then we can do ROS2 run Viam Rover motor control to start our ROS node. If you remember from the code, there is a ROS log output to tell you that the motor control watchdog has timed out. So it started in that state, and therefore nothing's going to move until we get that first command. If we go to another screen or another terminal, we can now look to see, okay, what is our list of nodes? And we'll see that there is this motor control node running. We can do info on motor control. It'll tell us that it subscribes to this command vel topic, and then a bunch of standard ROS2 node things, such as ROS out and describe parameters, etc. So now we want to test this vehicle, and the way we're going to do that is using the turtle sim. So in one of the standard ROS2 tutorial guide topics, they talk about turtle sim. And turtle sim is a couple of packages. It creates a little graphical interface, and then also a keystroke based teleop command control to move this simulated turtle around in this simulated environment. Now, one of the nice things about this is that it's two separate nodes. So there's the sim part, and then there's the control part. And for this video today, we're just going to use the control part in order to command our vehicle. The part we're going to care about is this turtle teleop key node, and we're going to do some remapping to map it to our specific topic, because by default the turtle sim teleop node is going to target a very specific topic, but our topic is different. So you'll have to install the turtle sim functionality as part of your ROS2 install in order to do this part of the video. So we're running our motor control node, and then we want to run our turtle sim in order to control it. So we'll see we run the turtle sim, the turtle teleop key node, and then we remap the turtle1 command vel topic into our standard topic. So now we can show the vehicle moving, and we will use the turtle sim teleop node to control the vehicle. So we have two screens showing here, and the top shows the output from the Viam Rover motor control output node, and then we have the turtle sim teleop key, and we can see the vehicle will move when we send the command. So if I go forward, it moves forward, go backwards, it moves backwards. We can turn left and right, and if we simply don't do anything, eventually it will time out and the vehicle will stop. So very basic control right now, where it's kind of hard to get exact control, but it shows the basic motion for now. And then we have our first attempts at using ROS2 to control the Viam Rover. I'm hoping to have this be a bit of a series where we can incorporate more of the Viam Rover functionality, such as the wheel encoders, the accelerometer, and the camera, and start incorporating some more of the more advanced ROS2 packages to show more advanced functionality. I hope you enjoyed this video. That's it for now. Talk to you soon. Later.